Hi everyone. Okay, so I'll start presentation. So today I will first talk about multivariate distribution, including multivariate normal distribution. And then I will talk about some fraction and matrix model, some linear algebra. And then if I have time, I'll cover matrix analysis, matrix and variable. So let's first start with multivariate distribution. So you have a random variable x. Now it's a d-dimensional variable. And here we will just assume this vector belongs to like a d-dimensional Euclidean space. So every entry of this vector is a number. So it's a random vector, and we only consider those distributions with PDF. So this means you will have this. You will have a function. Oh, by the way, interrupt me whenever you don't understand, because I don't know like what topics you are familiar with and this topic. So it will be a function that takes d numbers, and you will get a probability. So for example, like if these are discrete variables, you will have for example one way to define this PDF, this density function is it's just a constant function. This means I will have two real numbers that is drawn uniformly at random from the region of -1 and +1. So it's like this. This is x1, this is x2. And this probability density function must integrate to 1. So this means it must satisfy this function satisfies this property. And if you have more than two variables, it will be like this. So this multi-integration should integrate to 1. Okay, so this is a kind of a definition of a multivariate random vector. So we can use some quantities to characterize a multivariate distribution. One of the most important quantities is expectation. So for example, if I have a d-dimensional random vector, the expectation of x, this will also be a d-dimensional vector, but this will be a deterministic one. So it's not a random variable. So this is defined as this. So basically taking the expectation of every dimension. Before proceeding, I want to add something. So this is taking expectation with respect to one variable. So this is what we call a marginal distribution. So let's consider again in this example. So I have two variables. So this function defines a distribution over two variables. What if I'm interested in only one variable? So what if I'm interested in only this one variable? What would be the distribution of this univariate variable in this case?
Just the entire distribution, take the partial derivative of x.
Partial derivative of x? Oh, you mean... so let's go back to this. So I have two variables. And at each sampling, I will get a point that is randomly in this square. So what if I only care about this variable? Like every time I get x1, x2, I discard x2 and I only care about x1. What would be the distribution of x1? That should still, and in this example, it should still be the uniform distribution on the interval minus 1 positive 1. Because like no matter what the value of x2 is, the x1 should still be uniformly distributed on this interval. So a formal mathematical definition is P of x1 if you integrate out the x2 variable. So let's define like this. So if you do the integration, you will see it's px1 is 1/2 because this is 2. It's 2 times 1/4 is 1/2. And you can see this is still a valid distribution because if you again integrate out this x1 variable, it will integrate to 1. So yeah, so this is what we call the marginal distribution. It means if you have a multivariate random vector and you like discard some part of this vector, like x1 to x3, you discard maybe from x3 to x3, and you only consider x1 or x2. The distribution of x1 and x2 will be the marginal distribution. That will be defined in this way. You integrate out all irrelevant variables to get a distribution of the variables you are interested in. So is this clear? So if this is clear, then this should be easy to understand. It's just the expectation of each of the marginal distributions of xi. So like in this case, it will be like it will be 0 because both x1 and x2 are uniformly distributed on this -1 and positive 1. So the expectation should be both 0. So this is expectation. Another thing is called the covariance. So you must know the variance of a univariate random variable. So the variance is, if this is a number, then it will be it will also be a number. It's the expectation of the variable, the square of the variable minus its mean. But in multivariate case, the covariance will be a matrix. This matrix will be d by d. And the ith entry, the ith row and the jth column, this one will be the covariance between xi and xj. And is defined as expectation of x minus xi minus xi and alternatively we can write this as expectation of xi xj minus And you can see if I is equal to j, then the covariance of xi and xi itself will be just the variance of xi. Yes?
Can you explain what the vector of expected values means? Are those just marginal expected values? I don't quite understand the
Which one?
intuition.
What does this mean?
Yeah. What is the intuition behind it?
It's kind of like this x is d-dimensional, and I want to ask what is what is this vector on average? So then I will get, certainly I will get a vector, right? And for example, the first entry of this vector is like, what is the average value of xy? And this shouldn't depend on x2 and x3.
Oh, so it's just independent of the other variables.
No, we don't assume independence. This definition holds for all random vectors.
Okay.
Yeah.
So if we had to calculate E of x2, we would just marginalize.
Yeah, this is one way to calculate. Or by definition, the definition should be the integration of x. But if you evaluate this integration for xi, then it will be and a lot of everything else, and you integrate out all the other things, it will be the marginal distribution. So this is how it is. So we are at this covariance thing. So some facts about this covariance matrix. The diagonals of this covariance matrix will be just the variance of each. This will be variance of x1, and this will be variance of x2. And the variance of each variable. And again, this is defined on the marginal distribution. So whenever I wrote this, if you only have two vectors, it will be the marginal distribution of these two vectors. So yeah, and this diagonal is always larger than or equal to 0. So this is the first observation. And also this matrix is symmetric. That this will be equal to this. Because the one-dimensional, like the real number, the multiplication of real number is coming, so this will be a symmetric matrix. One interesting case is when this covariance matrix is diagonal, it means it's 0 for all the off-diagonal elements. So this is a very interesting covariance matrix. This is what we call uncorrelated variables. I note a very interesting question asked this morning on Piazza. So this only means these d variables are uncorrelated, but it doesn't mean they are independent. It doesn't even mean they are pairwise independent. So, so do you know how independence is defined and how correlation is defined for multivariate variables? Okay, I will see that. So, so I have this multivariate function. If this is factorized, this is called independence. So if this holds true for all x1 to xd, all values of x1 to xd, then we say the d random variables are independent. So this is independent. If this is true, that would so if the marginal distribution of any pair of variables factorized, like can be expressed as a product, and if this holds true for every pair of I and J, then we say they are pairwise independent. Independence will imply pairwise independence, but the reverse is not true. You can find pairwise independent variables that are not independent. And as we, an even weaker notion is uncorrelated. That means Nij. So for any pair of I and J, the expectation of the product equals the product of the expectations. This is then, if this holds true, we say xi and xj are uncorrelated. Pairwise independence will imply uncorrelated, but not the reverse. You can find uncorrelated variables that are dependent. One example is if you consider x is a one-dimensional normal distribution. V is like V equals 1 with probability 1/2 equals -1 with probability 1/2. And you define y equals x times v. So I first draw a Gaussian variable x, and then with half the probability, I flip the sign. So in this case, x and y will be uncorrelated. You can do the calculation. The expectation of xy will be the same as the expectation of x times the expectation of y. Actually, they are like both sides will be 0. But certainly x and y are not independent, because if you know y, you have some information about it. If you know y, you know x is either y or minus y. So x and y are not independent, but they are uncorrelated. So yeah, so if the covariance matrix is a diagonal matrix, it means your x1 to xd, your d variables are uncorrelated. Okay. So another concept is conditional distribution. So we have the marginal distribution. The conditional distribution is for example, if we have P of x1, x2, the probability of P of x1 conditional x2 equals A is defined as P of x1 divided by P of A. This is the marginal distribution over x2. So yeah, so this will be a distribution over x1. It's conditional x2 equals A, then you divide your joint distribution by the marginal distribution of the variable you're conditional. Like for example, in this case, we can ask what is the distribution of like x1 equals x1. What will be the distribution of x1 conditional x2 equals 1/3? So you can do the calculation, and you will find out this x1 will still be the uniform distribution over the interval of -1 and +1. So this is another characterization of independence. If this distribution does not depend on the value of x2, we will say x1 and x2 are independent in this case. So the intuition is conditional on the fact that I know x2, I get no information about x1. then x1 and x2 will be yes.
Go ahead.
Is there a simple real life example of variables that are ungovernable for not independent?
So since this example is not real life. Okay, I'll explain it again.
No, I mean that's
Yeah.
that's a math example. Right?
Oh, let me think. Well, for real life example, how do you define expectation? This is kind of let me think.
Like even roughly something like that.
Because to be honest, independence is like a real life concept. Like you can very easily find examples that are independent or not. But this correlation is really a math concept.
Right. Yeah.
Yeah, it's like, for example, when you do linear regression, you will see like this uncorrelation. But they are only like this correlation concept is really linear.
Right.
So if like they are like so for example if x and y are uncorrelated, what about x squared and y squared? They may be correlated or maybe not. But if x and y are independent, then x squared and y squared are also independent. So this transform will preserve independence, but will not preserve correlation because correlation is really like a linear concept. Okay. Okay. Your question?
Oh, well, you just wiped it. I was
Oh, sorry.
hoping the. So what is the P of that A?
Oh, you are. So
Given
it's the
that-
continual.
Given the case on the right hand side, it's so it's just a short form of bx2 equal to A.
This one?
Yeah.
Yeah. This is just short form here.
Okay. Yeah.
This is.
Okay.
So if you plug in like x1 equals b, this will be.
Yeah.
Okay. Any other questions? Okay. So one most important and I think is perhaps the only example you will see for multivariate distribution is the multivariate Gaussian distribution. Because to be honest, all the other distributions are intractable, which means you cannot sample efficiently from the joint distribution unless they are independent. Not even the Bernoulli distribution. But the multivariate Gaussian distribution is something we can sample from for every mu and every sigma. And I will tell you how to sample from a multivariate distribution at the end of this. So the multivariate Gaussian distribution is parameterized by two parameters. One is the mean vector, and the other one is the covariance matrix. So this is the vector sigma D. This is the positive semi-definite matrix of D by D. So we usually abbreviate this as N. So this N is normal, this D means D-dimensional. This is the mean, this is the covariance. And this will uniquely define a multivariate Gaussian distribution. So the PDF, like the density function, is written as so this is a determinant of the positive semi-definite matrix sigma. You all know about determinant, right? So, and here we are assuming sigma is positive definite, we are assuming sigma is invertible. If sigma is, yes,
Should that be plus half
which one?
in the power? How the determinant?
Oh, sorry. Yeah. So, yeah. So we assume sigma is invertible, which means the determinant is not zero. If determinant is zero and sigma is not invertible, this thing will, it will be complicated. It's called, I think it's called, I don't remember the name. So if sigma is not full rank, this thing will become the fusion index. And but we will focus on the case where sigma is full rank, so sigma is invertible. So this is similar to the one-dimensional case, right? In the one-dimensional case, the sigma will just be a number. It will be the variance. So this will become 2 pi sigma square root over 1. And this thing will become x minus mu squared divided by 2 sigma squared. Sigma squared is the value. So when d equals 1, it will reduce to the one-dimensional Gaussian case. And for general d, this will be the definition of a multivariate Gaussian distribution. So let's first see some of its properties. So two simplest properties, the expectation of x. What will be the expectation of x? That will be mu. Right? And the variance of x will be sigma. Yeah, so because this is by definition. And some special cases. So for example, if D is 2, it's two-dimensional multivariate distribution. Yeah, let me actually ask this question. If D equals 2, how many parameters are there in this multivariate distribution? I don't know. 7? Any other answers? 4? 5. It should be 5. So it's parameterized by. So the mean has 2 parameters. Nobody questioned this, right? The thing is the variance. Remember, these two should be the same. So it's 1, 2, 3, 4, 5. 5 parameters. Because the variance must be symmetric. And this, conventionally, we will write this as rho sigma sigma y. Because sigma x, sigma y must be larger than 0. Must be positive. Otherwise, it will be low rank. It will not be invertible. So this rho is actually very interesting. If you write out rho, it will be defined as the covariance of x1, x2 divided by the variance of x1 and the variance of x2 square root. This covariance, remember, we defined it as equation of in some textbooks, you will see this definition as the correlation coefficient between x1 and x2. And if the correlation is 0, then we will have 0 on the left side of entries. The x1 and x2 will be uncorrelated. So let's just do more. So this is a special case of two-dimensional Gaussian.
Yes? Just hold on for a second.
Sorry.
Can you rewrite the last one?
This one. This is
Thank you.
okay. So so some interesting facts about the multivariate Gaussian distribution is first, the marginalization of a multivariate Gaussian distribution is also a Gaussian distribution. So let's say in this example, what would be the marginal distribution of x? That will be a Gaussian distribution of mean mu x and variance sigma x squared. And what would be the marginal distribution of y would be mean mu y and variance sigma y squared. So in general, when you have a multivariate Gaussian distribution and you want to know the marginal distribution of a subset of the variables, you just read out the subset in the mu vector and the subset, like the subsets in the covariance matrix. You extract this matrix, that will be your mu Gaussian. So any marginal monotonalization of a multivariate Gaussian is also a Gaussian distribution. So this is the first property there. Another property is the conditional distribution of a multivariate Gaussian is still a multivariate Gaussian. So let's say we are interested in this distribution. So what would be the distribution of x conditioned on y equals small y? This is still a Gaussian distribution. And actually we have a formula for this. So in this case, it will be a Gaussian of mu bar squared, and this mu bar will be mu x plus and the variance will be so if you simplify it, it will be so in general cases where you have more than one variable, this will be the inverse. And this will be an inverse instead of divided. Both these formulations can be found on the Wikipedia page. Yes?
Should it be 1 minus del square?
Which one?
No, variance, the condition.
sigma 1, 2 square.
The 1 minus the square.
Oh, yes, sorry, yeah. You have two rows. Yeah. So the general story is like the marginalization and the conditional distribution of the multivariate Gaussian are still multivariate Gaussians.
So the variance doesn't depend on the value of y.
The variance doesn't depend on the value of y. No. No, it didn't. Okay, one last example about multivariate Gaussian, which is a very important example, is any affine transform of a multivariate Gaussian distribution is still a multivariate Gaussian. So for example, if x by affine transform, I mean y is b x plus b. B is a matrix, maybe a rectangle matrix, and C is a vector. So for any B and C, this Y will still be a multivariate Gaussian. And the formula is actually very easy to remember. Mu tilde will be B mu plus C. And sigma tilde will be B. This is actually very easy to verify, right? You take an expectation, C can be pulled out, and B is a constant, P can be pulled out too. Right, the variance can be verified in a similar manner. So this means for any affine transform of a multivariate Gaussian, I can get the result random variable still follows a multivariate Gaussian distribution. So this fact is very important. You will see this a lot of times, and most important, that gives you a way to generate multivariate Gaussian distribution for general mu and sigma. So how many of you know how to generate a one-dimensional Gaussian variable other than running like rand n in MATLAB? So suppose you know how to generate variable uniformly distributed 0 and 1. How do you generate a Gaussian distribution? Or maybe I should ask a single question. So suppose you know how to generate one-dimensional Gaussian distribution. How do you generate a multivariate Gaussian distribution? So, like if you know how to generate a one-dimensional Gaussian distribution, you can easily generate any distribution of this form if sigma is a dipole matrix. Or maybe more simple if sigma is the identity. So this means you have the independent IID, so identical independently distributed Gaussian distributions. You can just generate x1 like x1 to xd, each of them from the n0 1. And then you add mu b, you add mu1. So this will be the This will be a multivariate Gaussian distribution with the identity as a covariance matrix. And now suppose you have the sigma here. You can use this trick, right? You can say, well, I want to find B such that BB transpose equals my sigma. So this B can be found using diagonalization or singular value decomposition. And once you find it, you can just generate the simple Gaussian distribution, and you multiply your vector by this capital B. Then you will get a distribution with any mu and any sigma you want. So this is one way to generate multivariate distribution with non-diagonal covariance from one dimensional Gaussian distribution. You don't need to remember it, it's just a fun. Okay. I think we are done with multivariate Gaussian distributions, and I have 15 minutes left. I'll briefly talk about vector and matrix norm, which should be easy. So norms. So let's say I have a vector x, which is x1 and x2. The norm of a vector is a function from the vector to a positive real number, and the norm function must satisfy three conditions. The first condition is x larger than 0, larger than 0, and if x norm equals to 0, if and only if x is 0. Second, a times x, if a is a scalar, is a real number, will be the absolute value of 3 times the norm of x. And third, the triangle equation. If y norm is smaller than x plus y norm. So any function satisfying these three conditions will be a norm function. So the most widely used norm, and I think the only norm, the only vector norm you will see is the vector p norm. For every p in there, infinity defined as the sum of dx on p. So this is the vector p norm. Some special case is p equals 1. It's called vector 1 norm. The sum of the absolute values. P equals 2 is the most widely used case. Is x2 is and if you read a paper, you see a vector norm without specifying the value of p, that will be p equals 2. This is like the convention in writing. If you don't specify the norm, that will be 2 norm. And some extensions. So this is defined for any value in 0 and infinity. But actually, the most interesting thing is when p equals 0, p equals infinity. P equals infinity, the x infinity norm. It's also very like widely used. With the mass of the absolute value of x. It's an infinity norm. P equals 0. The 0 norm. You will see this not very often, but still sometimes. Is the number of non-zero elements in x. So I think these two norms, these four types of norms are the only vector norms you will see in machine learning. And this norm is the most, this two norm is the most, the most widely used. So people usually omit these two in their writings. So these are vector norms. Any questions? Yes?
Sorry, I think P must greater than 1 to satisfy the third condition.
To set the third condition.
As if P is 0, then X and minus X.
You should.
Yeah.
It's smaller than
If P is 0, then X is and Y is equal to negative X.
y is equal to negative x. Then this will be 0, this will be 2x. But you did make a point, so the p plus 1 is actually another important turning point. For everything p larger than or equal to 1, it's convex. And for p smaller than 1, it's not convex. But it's math. That's another reason why you don't see p smaller than 1 in machine learning at all. Because no convex functions cannot be optimized. But for anything like p in, this vector p norm is verified. Other questions? Yes?
What's the value here?
Which one?
The last one, P equals 0, some D equals 1 or big I.
This I?
No, the 1.
This one?
No, that's 1. Oh, that's a 1.
Which?
No, next xi
So
is
it's
0.
zero.
Sorry.
The indicator.
Oh, this is indicator function. So if xi is not 0, it will be 1. If xi is 0, it will be 0. That's how many non-zero elements in this vector. Okay, so this is vector norms. And for vector norm, we can become matrix norms. For matrix norms, again, that should satisfy these three conditions. Except this time, instead of having x, I will have matrix elements. And this A and B should be of the same dimension. However, for matrix norms, there are another property which is not satisfied by all matrix norms. It's called like submultiplicity. So A times B norm is smaller than A norm times B norm. This is not satisfied by all matrix norms. If a matrix norm satisfies it, it's called compatible norm. Almost all matrix norms you will see in machine learning will be compatible, except for one special case, which is a max norm. I will get to that soon. So matrix norms can be roughly divided into three classes. The first class is we call induced norms. Induced norms. And the second is introverted norms. And also there's something called I don't know how to say. I personally call it trace norm, but this will be more advanced, and I will talk about these two norms first. So the induced norms is defined as this. So the P induced norm of A is the supreme of x not 0 in x. Divided by
And what's the supreme here?
the supreme, it should run it in your freshman class. Okay, think about it as max. It's the same as max, but it's like max over an infinite number of numbers, so you don't really attain it. Yeah, I can only explain this to this precision because if you want me to try to explain delta, you will go crazy. You think about it as max. So think about all the vectors x. And for every x, you will compute this. This is a number. And for all the x, you will get the largest one. So this is a definition of the p-induced norm of A. Alternatively, you can write it like this. These are equivalent because the x p norm satisfies the multiplicity of a scalar. So you can, instead of maximizing over all vectors, you maximize over those vectors that have unit p norm. So for all vectors that have unit p norm, you compute this matrix vector product. This is a vector. This is a vector, right? A is a matrix, X is a vector. H is times vector is a vector. You compute the p norm of this vector, and you report the largest one. So this is matrix p norm, induced p norm. This can be defined for p, again for p from 0 to infinity. Okay.
So any x will work?
Which one?
Like for that the vector x that's involved, you can just choose any x as
No. You choose this x so that this one is maximized. This is a definition.
Okay.
This is a number. This is a number.
Yes.
Yeah. So for every x, you report the largest number. So this is the definition of the induced norm. It's a little bit more involved than vector norm, but it's based on vector norms. So special cases. Again, these 4 special cases, and you should remember them. The most important case, p equals 2. Look, I have ignored the 2 here, because if I don't write it as 2. So this is the matrix 2 norm. And do you know eigenvalues, eigenvector? So it will be the same as the largest eigenvalue of A transpose A. Yeah, and if you know singular value decomposition, that will be sigma max. The largest singular value of A, no matter on what whether A is square or not. So, and again, because this thing is so widely used, if you see this, that will be matrix 2 norms. So if paper didn't specify what norm it is, it's the matrix 2 norms. This is called 2 norm or spectrum norm. One reminder, don't confuse this norm with this. There is another norm which is defined as the sum of all the matrix entries square root. This is like the vectorized definition. Like this is different from the matrix 2 norm. These 2 things are not the same. So if you see A 2 norm, don't confuse it with this one. This one has its own name. It's called Frobenius norm. This one is called 2 norm or spectrum norm. So to illustrate this, think about an orthogonal matrix U. If U is, do you know orthogonal matrix? U transpose U is U transpose is that. So this is called orthogonal matrix. So if I ask you what is the 2 norm of U, what would be the 2 norm of U? 1. What would be the Frobenius norm of it? Square root of d. It's square root of d, right? Because every column is sum to 1, the square sum to 1. So the entire matrix sum to d and the square root is square root. So they are very different. Actually, Frobenius norm is always larger than the two norm. And the two things are equal if the matrix is rank 1. So the Frobenius norm can be written as the sum of the singular value square, okay, divided square root. So it's always larger than this two norm. So this Frobenius norm is one example of the entry-wise norm because it's like entry-wise. Yes.
So it's kind of obvious that the two norm is just like the potential stretch vector. Like, what does the entry-wise norm like?
What does this
matrix
norm?
like?
What does entry-wise norm mean? It's just a norm.
Is there a way to understand it?
Okay, if you want to understand better. So for me, there are only two entry-wise norms. One is the Frobenius norm, and the one is the max norm. So this one should be fairly easy to understand. It's just the largest element in your matrix. So for the Frobenius norm, if you really want to understand it, I suggest you understand from this direction. So it's the sum of the squared singular values. And this two norm is the largest singular value. So it's kind of like the two norm is the vector maximum in the trace space, in the singular value space. And the Frobenius norm is a two norm in the singular value space. So yeah, this is a little bit advanced. It's actually a nice connection. So we have two norms, we have Frobenius norms, and I just want to mention two other norms, and we are done. So like matrix one norm, and they are all induced norms now. One norm is so you sum of all the columns, the average values from all the columns, and you pick the largest one. And the infinite norm is the opposite. You sum over all rows, and you pick the largest row. So this is usually called the column norm, column max norm, and this is the row max norm. They are all induced norms. And like I said, you have the Frobenius norm already defined, and you have the max norm, which is for max A final remark is, like all induced norms, like the spectral norm, the one norm, the infinite norm, all these norms are compatible. All induced norms are compatible. And the Frobenius norm is also compatible, but the max norm is one exception, it's not compatible. So don't try to write equations like this. So think about a counter example. This is certainly not true. But I once made the narrow like this. But this is true. So these are vector two norms. This is matrix two norm. This is true. Like this is by definition true. You can work out the definition, but this is not. Okay, so I think we don't have time now. So something I didn't cover today is like diagonalization, which is diagonalization, right? X equals a u central. Do anybody don't know this? Is it everyone know this now?
Just forgot it.
What? Oh, that, yeah. Yeah, there's something like that. Yeah, that's easy. They are very important concepts in English. So just back to your question, those two notes can be very well understood with this one. Like this sigma is sigma 1, and this sigma 1. So the forbidden norm will be squared, and the two norm will be the largest one. Then you can even define a one norm on this, so this is very nice. Anyway, I think we'll spend like 10 or 20 minutes to cover the next recitation. And also something related to matrix differentials. You can find this concept in the last week I put down there. Okay, thanks.
Doesn't want.